And welcome back. Now today we're going to be making a little bit more progress on the components that need to be built into this buggy, and in fact it's this HC SR04 ultrasonic transmitter and receiver that I've bolted on the front here. More about what I've done with this a little bit later. But what happened was I put this on the front and I thought, right, I'll just go and grab the code then that obviously I've done in the previous demo and just plug that in. And guess what? I have never done a demo on this device, and I couldn't believe it, frankly. It's one of the sort of fundamental basics, isn't it, of an Arduino system, some kind of ultrasonic detector. So, well, let's go and talk about the HCSR04 in its simplest of forms, and you can see I've got quite a few down here, including some of the mounting brackets. I've even got an Arduino hooked up to this one, just with a little sketch on it. And what we'll do, we'll first of all look at how you would write it sort of natively without a library, really, okay, just so that we understand what it is that it's doing it. Then we'll abandon all that because there's a very good reason why we should be using a library in this case. And, well, just see what the improvement is. And then we can talk a little bit more about some of these mounting brackets I've got here, the pack of 5 ultrasonics here, and where I got them from, and where, in fact, I should have bought them from instead. And then we'll talk a bit more about this buggy. And well, there's been some discussion on the previous videos about this buggy, about the orientation of this, about basically which direction it should be going in. Is that forward or is that forward? You know what I mean? So that was interesting. So we'll talk about that towards the end of the video, but let's scoot on ahead and first of all look at how we can get this Arduino with a simple HCSR04, which yes, I have put into this mounting bracket, 3D printed mounting bracket, and just see what it does. Okay, right, let's call up the code window next. Let's just talk through the code then. I've cleared the decks a little bit down here so we can see a bit more what's happening. I've plugged it into this Arduino. Now, as you can see, this Arduino here is in fact an Uno clone, a proper Uno clone, rather than my Nano that I'd normally use. So I'm having to use this really big, thick, full-size cable connector at the back, and it's trying to twist the cable and flip this over. So I've stuck this down with some blue tack, and right, I'm hoping it will be stable for us. So let's look at the sketch then from the word go. So what are we doing here? Right, ignore these first 2 lines. We'll talk about those a little bit later. Right, all we need to do is define which pins you want to use on here for the trigger and the echo. If we just zoom in on that a little bit, as you can see, this has got 4 pins on it. VCC and ground, so that's 5 volt, that's pretty easy. And then 2 pins, one's the trigger, which is an output pin as far as your Arduino is concerned, and the echo pin, which is an input pin as far as your Arduino is concerned. Now there are some units like this with a single device. So if you can imagine half of that, just that, and then you wouldn't have an echo and a trigger, you just have 1 pin, so it'd be a 3-pin device. And they work okay. What it would mean in your code is that you transmit and receive on the same item, but well, I say the problem, it's not really a problem, but I mean obviously it's that switching delay is obviously going to affect the sensitivity at very close distances. So this one goes down to about 3 centimeters, something like that. So, and of course these ones are, well, readily available, ubiquitous even. HCSR04. So back to the code. So we've defined 2 arbitrary output pins, just 8 and 9, just randomly. We must define a timeout. That is, when this device transmits, how long does it wait for before it goes, do you know what, I didn't receive anything. Think of you know, a submarine sonar. So it sends out its ping, and then what? It just waits and waits and waits forever. Because if you're not careful, of course, it would wait forever and be stuck in a loop. Well, luckily, the code we're using times out after a while. Now, I've put in here 20,000 milliseconds, which is 20,000 microseconds, which is 20 milliseconds. More than long enough. I mean, that would measure, you know, a couple of meters or so, which is far too long actually for what we want. But this is just a demo. We then decide whether we're going to, whether the resultant value that comes out of here, of course, isn't in any particular unit of measure. So we have to decide, do we want centimeters or do we want inches? And I've just ruined the code. Let me just put that back. There we are. And this conversion factor will hold one of these conversion values. Okay, so depending on where you are in the world, you may decide inches of hue rather than centimetres. And if you're in the UK, you'll probably use both interchangeably. Right, so as I said, we use the trigger pin as an output and the echo pin as an input, which sort of makes sense, doesn't it? You're sending out a pulse and then trying to read something back in. So to send out a pulse, first of all, we set the trigger to low and just wait for 2 seconds. This is sort of, I don't know, it's sort of best practice really. I don't quite understand why we need to do it, except that everybody says you do need to do it, including Arduino themselves, just to let things settle. It's only for 2 microseconds, so it's not very long, is it? Then we set the trigger pin on here to high for 10 microseconds. Not a long time at all, just to give it that little ping. And then we set it to low so that it stops. Then we use a built-in feature of the Arduino language called pulse in. All right. Now, forget the fact I've got RSB on the front of that, my initials. Just ignore that. The actual Arduino version is called pulse in. There's our pin that we want to read from. We're waiting for it to go high, and there's the timeout value of 20 milliseconds or 20,000 microseconds. Now, when that comes back, if it comes back as 0, it means it timed out. It never received a reply in that time frame. But if it did come back, now I've called my variable here distance. That's not really right, is it? It's just a value. But what it means is if you divide it by the conversion factor, which we've said is centimetres or inches, and then divide by 2, because obviously it's going, this pulse is going out and then coming back. We don't want the distance of the entire traversal of that sound. We just want the one-way measurement. Okay, that's what we divide by 2. And then for demo purposes, we have a blocking delay for 250 milliseconds, quarter of a second. And, well, that's it, really. So, I do believe it's... Let's have a look. Is it running or is it not running? No, it's not running at the minute. It is running, but the debug window, which is partially hidden by my face, actually, and indeed the workshop. Let me kill a couple of these windows here. Right, we'll just add this COM port on. Ah, there we are. So right, now we're getting this value. Now these values are in centimetres, because that's what I've chosen. So 30 is about a foot. Now if I move all this stuff off my desk out of the way, it should go up. No, that's 2.9 meters now, because it's finding something across the other side of the room. Now let's think about this just for a second. If this was on a buggy like this with this code, why on earth would you want to detect things 2.9 meters away? And in fact, is it back? Yeah, it would be 2. It's right over in the corner. It's detecting it. That's far too far, which means our timeout value, this one here, is far too big, isn't it? It's waited too long to get a result. We really want to restrict the amount of distance that it can detect to about, I don't know, a foot, 30 centimetres, maybe 18 inches, 45 centimetres, something like that. Yeah, certainly no more than that, because what is the point? And it slows things down if it has to wait for that long. So what we should really do, just to be absolutely sure, is I think we could probably bring that down to something like 5,000 microseconds. So let's do that. 5, delete, and upload. And it's, do you want to build? Yes, I do. Thank you. Right, off it goes. This is the Eclipse IDE, by the way. Please don't ask me to do a video on it. It's just... Right, okay, that's running. And now let's have a look. Ah, good. Now what that's doing, you see, if it doesn't get a response, if we look at the code, it's saying if the distance isn't 0, print it out, otherwise don't. Well, it's not printing anything out at the moment, is it? Because the distance now is beyond the timeout factor. So let's see what that is. So if I put my hand, there, my hand's, well, about 50 centimetres away. If I increase that, all right, 74, that's it. So it's about 75-ish centimetres away from it, which is plenty, absolutely plenty. All right, good. Okay, I would say that's working. And now, what I'd also say is, we've written this code now and sort of hard-coded it. We've done all this rather than calling some sort of library. Why is that? Well, that's just to prove how it works. Okay, we now understand that by setting the trigger pin high for 10 microseconds. It's enough to give a ping out of this unit, and then we use the Arduino's pulse in function to receive the reply instead of using a library. But we will in a minute. But you might be asking at this point, hang on a minute, that's not really natively written then, is it? If you're using this pulse in that comes as part of the Arduino system, that's not actually writing it in the same way, say, that we've written this, natively. Okay, I understand what you're saying. So let me switch to a different view so you can see some of the pop-up windows of things I get with this IDE, and you'll understand exactly why we haven't written our own, believe me. Right, so now we're looking at the monitor view rather than the window view, so you can see all sorts of different things. RSB pulse in. Now I said ignore the fact there's RSB there, but as you can see, when I hover over features like this, it tells us what the underlying code is. And all I've done is found out where that pulse in code was and copied it verbatim to slightly lower down the code here. Right, so this isn't my code, this is just copied in verbatim, because I thought, well, we'll copy it in and just see what it is that this pulse in is doing. Now, even this little bit, I mean, do you really think a beginner is going to understand, well, this bit here, for example, digital pin to bit mask, digital pin to port, setting the state mask, doing all this, and then, look at this one here, count pulse ASM. This is an assembler function. Yep. Assembler function, so nobody's going to write that. I don't think I could, frankly. I used to write assembler for PICs, but that was some time ago. Basically, it's all a bit complicated, and this count pulse ASM, you'll find that in that library we had right at the top. Look, it says wiring private. I'm guessing the private is don't go and use this stuff independently, because it's really part of the Arduino system. Obviously, there's nothing to stop you using it, but why would you? So that's one reason why we're using pulse in, okay? Because it's just basically too complicated to write your own code to wait for a response here. That's not saying you couldn't, but if you want performant code that doesn't take, a tenth of a second to receive a pulse, and therefore you couldn't receive something more than about a foot away, well, you need really fast code, and that means, in this case, certainly, writing it in assembler. And we're not even going to look at that code because it's quite difficult. In fact, all these things on here now will pop up. Look, if I hover over delay in microseconds, for example, this is the underlying code that Arduino has supplied for us. Good old Arduino. This is saying, right, delay microseconds. If the frequency of the CPU is 24 meg, well, it's not. We normally run on 16. There's 20. No. There we are. There's our 16. So our CPU normally runs on 16, and it's saying, okay, a couple of if statements. Oh no, set up the microseconds. If it does all this for 12 meg, for 8 meg. Look at all this code just for delay microseconds. And down the bottom, look, it's actually running an assembler piece of code as well. This is assembler, and that means basically, okay, label 1. Subtract immediate from word, whatever these values are. Branch if not equal back to 1b backwards, so it branch back to here. So basically it goes down in this round and round and round this loop, which takes 2 cycles, it says, obviously using up time, microseconds. Now who's going to write that? Not me, and I would suspect most people watching this channel wouldn't want to write stuff in assembler. So that is the delay microseconds function supplied to us by Arduino as part of the Arduino IDE and language, and that's why we call these things at the higher level. It's brilliant, isn't it? Digital write. Now look at all this stuff that digital write does. Would you want to write that every time? Not me either. So there we are. That just shows you some of the stuff that is behind the scenes and why we are in fact using pulse in rather than all this stuff as part of the Arduino native core. Okay, we just don't want to go that far. However, having said that, we don't want all this stuff either, because whilst it works, and you can see it still measuring quite happily, look, my hand in front there, yeah, it's pretty quick. I mean, we are delaying it for a quarter of a second. It sort of falls over at about 3 though, I think. 4. Yeah, you see, look, 4 and 4. You can't get below 4. Oh, 3, lies, 3. just about anyway. But that's it, okay? Whilst it works, it's not the best way to do it. So let's plug in a library and see how much better that would be. Right, we're just uploading the new sketch and it's done. And right, so this is now using the NewPing library, as it shows you up here. The NewPing library is considered pretty much the de facto standard library for this device, and it's been written and revised over the years, and it's probably about as good as you're going to get it. So we've got the same pins defined now, though we can define the maximum distance in centimeters, that is, and we set up a new object like this by calling the NewPing class library, and then we just say go and get me my distance, basically sonar.ping in centimeters. There is one for inches as well, and then we're just printing it out as it's showing you in this area here. In fact, this area here that you can't quite see because there we are. Right, so it's down here that the output's been printed. So if I put something nice and hard and shiny in front of it, so there it is coming up, and I think you'll probably have the same restriction on here: 5, 4, 3. Yeah, see, it's then worrying about 3 and 5, 3 and 4, and the closer I go, see, I'm basically on top of it now, and it's getting a bit confused. It's probably bouncing about that sound a little bit, but from about 3 to 4 centimeters, it's extremely accurate, and it doesn't block. Well, the sonar.ping bit doesn't block. I'm blocking here with this delay, just so that we don't get a million outputs on the debugging stream. But apart from that, it's all refined to the nth degree. It works on many platforms, for Arduino. I think there might be a conversion now for various other ones like the ESP8266 and things like that. So anyway, that's the library that we're going to use on my buggy, because it just works. We don't have to think about it, and if anything goes wrong, it's not because of that code, that's for sure. It'll be my code. So that's how we do it. Now, is that not simple? And it's just a few lines of code, isn't it? There's hardly anything there, and it works. As you can see with me waving my hands about, that value down the bottom here keeps changing. And if I take my hand away entirely, it stops because we've got 0 back because it's exceeded the maximum distance. In principle, just the same as the previous sketch. Great, except now, of course, we can, rather than trying to work out how many microseconds something's going to take to come back, we can actually specify it in actual distance. Much better. Cool. That's great. Let's have a look then where I've got various bits and pieces and what else interesting we can talk about on here, because there's a number of things. Right, so as you can see on my workbench here, there's quite a few brackets. Now, I didn't know what sort of bracket I wanted to put on my buggy. Let me bring my buggy back into shot and just come back out of it. Right, so as you can see at the moment, I've screwed this HC SR4 device on a piece of strip board and just bolted it through because I wasn't really sure how well it's going to work. One thing I immediately discovered is that my buggy would go careering off across the room, and as it detected something, it would try and come to a halt, but wouldn't, and it'd come in it and smash this straight on its front and then bend it back. You can see how easily that bends. So I thought, right, there's a design failure there on my part. One, the ultrasonic device should not be sat forward of the leading edge, if indeed this is the leading edge rather than the trailing edge of the unit. That's the first thing. And secondly, the angle at which this is trying to detect is like 15 degrees. Well, that's absolutely tiny. So if this is careering across the room and there's something off at an angle here that it's going to hit because maybe it's coming at an angle, it just wouldn't detect it. Hence the pack of 5 that I bought to try and figure out how many I might need. Now, ideally, what I'd like to do is put one of these onto a servo and then mount that on the front, not overhanging like this, but on a servo, and then just scan backwards and forwards like this on a servo. And because with a servo, unlike a stepper motor, you know exactly the angle that you're at, you would know whether there's something on the left and you could move away from it, or something on the right and so forth. Nice idea, and maybe something I will progress in the future, but at the moment I just haven't got time to fiddle about with the servo code as well. That's sort of another video really, isn't it? So what I thought I'd do is maybe put a couple more of these devices sort of like that, one there and one the other side the same. Then of course I thought, how am I going to mount them? That was fiddly enough for a one-time job. Yeah, it would do. But I thought, no, there must be some mounting brackets, and lo and behold there were, as you can see. So I've got two different sorts here. One, now this one's been 3D printed by the looks of it from Maker's Hut. I'll show you where in a minute. And this one seems to be laser cut. Now I like this one because one, it's higher, so if I mount it on the side here, it's actually higher up, and therefore perhaps won't get bashed quite so easy, or I could even mount it that way round so that it's protected because it's set back a little bit further, and given that the minimum distance is about 3 centimeters, that wouldn't worry the fact that it's gone back a little bit. But also I like these because they were compact, and well, as per the one I'm using in my demo now, they've got a little cutout for the crystal at the top. Whoops. And oh yeah, that's coming off. And it's all nicely, you know, it's compact, and that will screw onto the board here somehow. So I didn't know which one to buy, so I bought both. Now these were, relatively speaking, quite expensive compared to the price that you can get them from the Far East, of course. Well, isn't everything? As was this pack of 5, which in fact I did buy via Amazon, but it was obviously some kind of, I'm guessing some kind of Chinese Far East import that they hold in Amazon warehouses. So let's just have a look where I got these from. Let's have a look at the browser. Here we are. So these are the, let me have a, these ones. Let me bring back my workbench. Right. So these ones are obviously these ones here. Okay, and I think they say they're 3D printed. Let's have a look. Yeah, 3D printed. There we are. Look. And you can, now you got the ones that I've got, which is vertical mount. You can't see the drop-down window there, but it's vertical mount or horizontal mount. And the horizontal was that other version here. I didn't want that one at all. I didn't think that was going to help, so I've chosen that one. That's fine. But you see, they're £1.39. The alternative then was that one. Okay, so that's this one here, and that's not 3D printed. I believe that one's, well, it doesn't actually tell me there, but mind you, £2.70. That's laser cut by the looks of it. Now, well, actually, one of the advantages of this one is that you can mount this either way up. Let me just bring back the workshop so you can see the where the crystal is at the top. Obviously, you want that's sitting proud of the board. So you can bring that in that way, or if you don't want it that way with the pins going down the bottom, you can easily turn that round, and there's a cutout down the bottom as well, and then you can have the pins going up. So it's a little bit more flexible than this one, which insists, if you're going to put it all the way through, that is, which insists that you have it that way up, obviously because the cutout's only at the top. But frankly, you don't have to put it all the way through, and of course this is friction mount. I mean, that is firm even as it is. So the fact it's got a cutout at the top there for the crystal, I don't think is like a big deal one way or the other. Obviously on my demo one here, oh, I thought I pushed it in further than that. Maybe not, maybe that's as far as it goes. Oh, that is it, yeah. But I couldn't turn it round the other way because there's no cutout. But as I say, I don't think I need to push it in that far. I mean, that is firm, even flush like that, which perhaps provides a more secure or protective mount for it. I don't know. Pays your money, takes your choice. Thing is, talking about money, well, oh, wrong window. Talking about money, $270 for that bracket. It's quite a lot of money, wasn't it? But I did want it quickly, having discovered I hadn't done a demo of this device before. And the other one was how much? £1.39. Now, if I'd been more patient and wanted them to come from a Far Eastern source, right, okay, this one here, so that particular laser cut one would have been 33p. Quite a difference, isn't there? Quite a difference. Might have taken anything between 2 and 4 weeks to reach me though, but at that price you could afford to buy, 6 or something, couldn't you, just in case they get broken, if you're going to crash into things. I don't know how resilient and strong these are yet. I haven't had a chance to use them. Let's talk about the actual unit itself. Now, I had a couple of these anyway, but I thought, well, I want a few more just to play about with. So I bought them from Amazon. Here we are. So these were £6.95 for 5. So you think, well, each one is not too bad then, is it? £1.30 or something. But if you go to the Far East and have a look, you can get 5 of them for £2.84. So that's quite a drop in price as well, isn't it? So there we are. What's this 5 pieces up here? Oh, here we are, £2.84. There we are. That was. So if I'd been a bit more planned in this particular video and a bit more patient, I would have saved quite a bit of money. But there we are. I'll have them now. So if I need any more, I'll know that next time I should order them in advance from the Far East. Good. So that's what I'm going to do then for this. Now let's talk about the actual buggy thing, because I haven't actually implemented any of this yet on it. Well, that's a lie. I have implemented that same sketch pretty much on here. Now, I don't want to talk too much about the rest of it, but I do want to think about which direction this is going in, because on the comments of the previous video, quite a few people have said, not in so many words, but they implied that in fact I was going the wrong way. This would be the way to go. So this is the front, and I'm thinking these slots here plus these mounting holes at the front could well take these sort of brackets a lot easier, or indeed these. I mean, these probably, and even, let's face it, if they haven't got the holes on here that you want, it's dead easy to drill them. I had to drill a couple of holes for the battery pack, which you may have noticed I've now swapped for 3 18650 batteries to bring me near enough 12 volts for this, the L298N. That's the bridge device from the previous video to control the 2 wheels, and from that we get a 5 volt back out on that purple cable going back into my Nano development board. So the Nano is also applied from this, and there's been no issue with noise from the motors or something upsetting it. It runs as it should do. But as I said, I do need more of these, so I'm going to put one there, move this probably to underneath or something, and put one in the front as well. But as I say, either set back a bit or turn round the other way to protect these devices so they don't keep smashing into things. Then I'll take that. Well, I don't know, actually, having thought about it, I might leave that one on there. So you have 4 devices. Have I got enough pins? Yes, I've probably got enough pins, GPIO pins that is, because when you reverse, as I've noticed of this one, when this one gets stuck in a corner, if all else fails, it says I'm trying to turn left and I can't do that. I'll turn right if I can. If that fails, I'm just going to reverse out. Well, of course, when it reverses out, it has no idea what's behind it, so it could easily just bash into things. Now, if I keep that one on the back there, that means it could also detect something at the back. So, in fact, yes, I've just decided that at this very second now, I'm going to keep that one at the back. Make this the front of the vehicle, though. Put that underneath. Have 3 of those at the front, rather than a single one on a servo, which brings a whole raft of design problems with it. And see how well that works. I think the cleverness, though, in any of these robot buggies is the algorithms you use in the code. Now, my code is fairly simple. It basically says if I get stuck, I'm going to reverse left or right and try and get out the situation. And if that doesn't work, I'm going to reverse and then try again. And it's sort of almost works, but it does get itself severely stuck sometimes, then just can't move anywhere. Not least of which is because it doesn't understand sometimes when the wheels aren't moving. So that's going to be a future video as well, how to detect via these little devices which came with this kit, and they go on the other end of that wheel here. They go on this spindle here, and they poke through that little slot at the top there, and there's a couple of detection devices, LM393s I think they are, that you put over this device like this, and it shines an infrared light through it, and then you can detect that revolution with an interrupt pin on your Arduino. So you'd need 2 interrupts on here, pins 2 and 3, because that's the only 2 interrupts you've got on a Nano or an Uno. Now you could in fact use a Mega here, and if you're immediately screaming, "Why, you've got to be kidding, a Mega is so big," is it? Is it? That's for a future video as well. We'll see what we can do about that. Anyway, that's all coming up for a future video. I'm going to now get on and start, well, I'll leave that one alone. I'm going to screw 3 on here, change the code. Hopefully I won't run out of pins on that. I don't think I've used that many at the moment. And see how far we get. But at least now we understand exactly what goes on inside these HC SR04 units. I've had a look at the brackets and the quite horrendous UK pricing in comparison to the Far East, but I did get them within about 2 or 3 days. So jobs are good in as far as I'm concerned. Great, hope you enjoyed that. It was fun doing, and thanks for watching, and I'll see you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.